Alright, today I am going to do the first paper of 2024 with you. So this is the February-March 2024. It's for mechanics and the zone is 4-2. Let's see what they've given us. Okay, question number 1. The displacement of a particle at time t after leaving a fixed point O is s meters. Okay, so just the first thing to note, this is a displacement time graph, not a velocity time graph. Normally they give us velocity, so now we just need to keep our heads about us. If I look at a displacement time graph, my acceleration, no, not my acceleration, my velocity is my gradient. Okay, so I need to just keep that in mind. There are 4 straight line sections. The particle travels 50 meters in the first 10 seconds and then at 2 meters per second. Okay, so the gradient of that line is 2 for a period of 10 seconds. The particle then comes to rest. Comes to rest for a period of 20 seconds before it returns when t is equal to 60. Okay, find the velocity of the particle during the last 20 seconds of its motion. Okay, so basically we need the gradient of this slope down here, but what I see is we don't yet know what is our displacement up here. That's going to help us to find the gradient of that line. So I'm first going to look at my second section, my second straight line section, and my gradient in this case is my change in displacement over change in time. I know that my gradient is 2, that's my velocity. So I'm going to just call that S, and then I'm going to say minus 50 over 20 minus 10. So I'm just working out the gradient between these 2 points, and in this case, because it's a velocity displacement time graph, I know that my gradient is velocity. Okay, so I'm getting a displacement of 70 meters up at the top here. Okay, and then I can do a similar thing for my last slope. My gradient is my gradient is my change in displacement over change in time. And in this case, it's going to be 70 over a change in time is 20. And it is going to be negative if I actually plug my zeros in the right place. So that is going to give us a velocity of minus 3.5 meters per second. Okay, so just make sure it's negative because they do ask for velocity, not for speed. So if they wanted speed, you would keep it 3.5, but if they want velocity, you need to change it. Okay, sketch a velocity time graph for the motion of the particle from 0 to 60. All right, so this is a bit different from the papers that we've seen in mechanics before. They generally give us velocity time graphs. In this case, they've given us displacement, so we just need to be careful. Okay, because I've got straight lines here, it means I've got constant velocity happening. So if I just look at my first, I might need to do another sum here. My first straight line section, my velocity is my distance of 50 over my time of 10. So that's going to be, sorry, that's 5, not 0.5. It's 5 meters per second. Right, so that's 5 meters per second. This is 0 meters per second, and this is minus 3.5 meters per second. So there we've got our 4 different constant velocities, and what that looks like on our graph is 1, 2, 3, 4. Let's just take 5 up here. So for the first 10 seconds of motion, so that's 10 seconds, we're going at 5 meters per second. Then for the next 10 seconds, it's 2 meters per second. Then we've got 0 happening down here for 20 meters per second. And then we've got negative 1, 2, 3, and a bit. Okay, so obviously it's just the idea. And that's going between 40 and 60. Okay, so I've maybe just dropped my lines here just to make clear. That is what it would look like if I've got sections of constant velocity. All right, let's jump into the next question. Okay, question number 2. A particle is projected vertically upwards from horizontal ground. The speed of the particle 2 seconds after it's projected is 5 meters per second. Okay, so we got projected motion. It's projected upwards at a certain speed. The speed of the particle 2 seconds later is 5. And it's traveling downwards. Oh, okay, that's interesting. So it's projected upwards, but 2 seconds later, it's already coming down. Okay. Find the speed of the projected particle. Okay, acceleration is -10. Okay, so I'm looking at this particle is going up and down. All right, so I'm going to take up as positive. You can do a Subot equation where it's going up and down. You can do that in one. Okay. So if I look at the variables that I have, I'm going to use my equation V is equal to U plus AT. And I'm just going to plug in my different values. So I've got a final velocity of -5, so it's coming down. I don't know my U. I'm going to take up as positive, so gravity is negative, and my time is 2 seconds. So what you need to realize is these equations of motion are vectors. So for example, if I was using my S, it would be displacement instead of distance. So long as you've got the sign in the right direction, they do kind of work out. What I want to say with acceleration here, if I take up as positive, I'm going to take up as positive, so gravity acts down as the particle is traveling up. So it's going to be decelerating, but it's going up. And then when it turns around, it accelerates, but it's now going in the opposite direction that I said is positive. So basically acceleration it remains negative, and you can actually do this. It works to do it in one arrow, if I can say that. Okay, so we have an initial velocity or initial speed of 15 meters per second. Right, and then find the distance traveled by the particle between the 2 times at which the speed is 10. Okay, so the speed is probably going to be 10 a little bit further down. So it's going to have a velocity of 10 and a velocity of 10. And they want us to find the distance traveled by the particles between these 2 times. Okay, so if I was to go between the pink arrows, I know my initial speed is 10, and my final speed is then going to be -10. I want to know what is the distance, and my acceleration is just always going to be gravity. Okay, so I've got -10 squared is equal to 10 squared, so those kind of cancel out. That's 2 times -10 times s. Okay, so what am I working out here? I'm working out my displacement. So that's not really going to work because it's just going to be 0, and that makes sense because it's starting and ending in the same place. Okay, so that doesn't work. So let's just go halfway up, and then we're going to have to divide it by 2. So it's just going to go up here, or more like we'll double it by 2. More like we'll just double it. Okay, so I'm going up, and then I'm going to say my velocity is 0 instead. So let's do that. So now I'm just going up my arrow. So my displacement here, or my distance, is 5 meters. And so therefore, because it has to go up and it has to come back down again, I know that it's then going to be 5 times 2, which is 10 meters. Okay, so interesting way of asking the question. Hopefully it won't throw you off at all. I find with those two-bit equations to draw the arrows and then to make sure your signs are all correct. Okay, next question. A crate of mass 600 kgs is being pulled up a slope of a rough plane. Okay. 600 kgs or 6,000 newtons. It's being pulled up a rough slope, so friction must act down at a constant speed. Okay, so my force that's pulling it up is going to be, I'm just going to also add my mg sine theta. Those are going to cancel each other out because it's a constant speed of 2 meters per second. Okay, by a rope attached to a winch. Plane is inclined at 30 degrees to the horizontal. The rope is parallel to the plane. The winch is working at 8,000 watt. Find the coefficient of friction. Okay, so that's what I'm looking for. Coefficient of friction between the crate and the plane. All right, if I just look in the y direction here, I've got my r, and there's only my weight component acting down, so it's just going to be opposite my weight component. Okay, so let's just maybe start somewhere. I'm going to start with the sum of my forces in the y direction should be 0. So I know I've got my r acting up and my weight component acting down. So that's going to be cos of 30. So r is 6,000 times cos 30. And that gives me 5196.15 Newton. Okay, that's my R value. Right, now let's work out the frictional force. So it's going at a constant speed. So I know that it's not accelerating. So it's actually going to be equal to 0. So I've got minus my friction, minus my weight component going down the slope. So it's mg sine of 30 plus my force pulling my crate up, and I just want to do power is force times velocity, my driving force times velocity. So my driving force is power divided by velocity. And so what that is 8,000 divided by 2. And that is equal to 0. Okay, so now I can work out my frictional force. And that's going to give me an answer of 1,000 newtons. Okay, and now I've got enough to work out my mu. So 1,000 is mu times r. And so my mu is 1,000 divided by 5196.15. And that gives me a value of 0.192. And that's to 3 significant figures, and there are no units for mu. Okay, so that's quite a nice question. What I recommend with these types of questions is you just have to start. You just have to start writing, and then it sort of falls into place as you figure out one thing after the next after the next. If you don't start, it's very hard to always see where the question is leading to. Okay, this looks like a forces and equilibrium question. We've got 4 forces act at a point. The magnitude of the forces are F, 2F, 3F, and 30. The directions of the forces are shown in the diagram. Given that the forces are all in equilibrium, find the value of F and theta. Okay, so this is straightforward. It's just going to be simultaneous equations. The confusing part is all the F's, but we should be able to do it. So I've got in my X direction, I've got my component of my 30. I've got my 3F going in the positive X direction. Here, if that is 45, that's also going to be 45 degrees. So I've got 2F cos of 45. It doesn't matter whether it's cos or sine of 45 because they are actually the same thing. Okay, and so here I've got, yes, I've got f is an unknown and theta is an unknown. So over here, let's just do one thing at a time. So I'm going to say 3f plus my cos 45, something you should actually know off by heart. Anyway, times 2, so that's going to be root 2f. So my f is 3 plus root 2f. Okay, sum of the forces in the y direction should be equal to 0. Sorry, this up here I wrote a bit strangely. Okay, sum of my forces in my y direction should be 0. So let's look, we've got 30 sine theta minus f minus 2f times cos of 45. That's equal to 0. Once again, I'm just going to collect my f's and my sine 30. Well, my sine theta is on the one side. And here I've got f plus root 2f. Okay, if I make f the subject of the formula, I have got 30 cos theta over 3 plus root 2 is equal to 30 sine theta over 1 plus root 2. Okay, so my 30s are going to cancel out. Then I'm going to divide sine by cos. And I'm going to take that to the other side. So my tan theta is equal to 1 plus root 2 over 3 plus root 2, which is basically 0.5469. And then if I can get the inverse of tan theta, my answer is 28.7 degrees. Okay, so that can feel like a little bit long to get there, but just keep going. I'm just working out my f now. 30 times sine theta divided by 1 plus root 2. And that gives me an answer of 5.96 newtons. That's 3 significant figures. Okay, so there we've worked out our theta and our f. I don't think there are many tricks to this. You just need to be careful with your f's, be careful with your angles, and then simultaneous equations. Okay, next question. This immediately when I see this, I can see it's kinematics and it's varying acceleration. Okay, so particle moves in a straight line from the point 0. The velocity of the particle t after leaving is given by that. So it's between 0 and 4, and it's a curved v velocity graph. You may assume that the velocity of the particle is positive. Yes, so the velocity is positive for t is less than a half. It's 0 at t is equal to a half, and it's negative for t is greater than a half. Okay, this is important information, I assume, otherwise they probably wouldn't give it to us. Okay, so a half seems to be the magic number. You may assume that velocity is positive. Okay, so it's positive, it's 0, and it's negative. Okay. That is useful if we're now going to work out displacement. We need to know where does it cross the x-axis. Okay, find the distance traveled between 0 and a half. Okay, right, so we are working with a curvy velocity graph. To find the distance, it's basically the area under the curve. In order to find the area under a curve, we need to integrate. Okay, so our integration is t3 minus 9 over 2 t squared plus 1. And we're going between 0 and a half. And they just said you can assume. So we just assume that the graph is above the curve and it doesn't matter. We don't have to prove that or not. Okay, so I've just integrated there. I might maybe before I plug anything in, t to the power 4 minus, this is going to become 3 over 2. A half and 0. If I plug in a half, and then I'm basically just going to minus 0, because if I plug 0 into each of those terms, it's going to be 0, but you must just make sure that you are correct about that. Sometimes it doesn't equal 0. Okay, so then I am getting an answer of 21 over 64 meters. Find the distance traveled, 21 over 64 meters, or 0.328125. It's interesting because that's actually an exact number, so I'm just going to put the whole value in, but I think you could leave it as a fraction, 21 over 64 meters. Okay, question number 2. Find the positive value of t at which the acceleration is 0. So that means it's a turning point on our velocity time graph, so we've got to differentiate the velocity time graph. And hence find the total distance traveled between t is equal to 0 and this instant. Okay, find the positive value for which the acceleration is 0. Right, so we need our velocity time graph. I'm just going to copy this. Okay, and we want to find where the acceleration is 0. So you must just think acceleration is change in velocity over change in time, and so therefore we are differentiating. Okay, that is acceleration, maybe acceleration in terms of t, and that is 3t squared times 2t. Now, other one falls away. Okay, and that value, to find the turning points, it must equal 0. So the way to solve this, I'm just going to take out a t. I should have taken out a 3t, but anyway. Okay, so 9 divided by 3 is 3. Okay, so the time at which this happens is 3, because we want the positive value. Okay, now find the total distance traveled between 0 and this instant. Okay, so our first part of motion we've already got between 0 and a half. So now we're going to go between a half and 3, and that we expect to get a negative answer because it's below the graph. Okay, I should not actually need to integrate again. I already have my integration. It might be worth doing it again if you want to just make sure that you're getting the same answer both times. I'm just going to plug this one in there. And I'm actually going to simplify this over here. Okay, and this, we're now going between 3 and a half. When I plugged in a half, my answer was 21 over 64. Okay, so I know that that's really going to be 21 over 64. That's a nice shortcut. Okay, minus 1.5 times 3 to the power 3 plus 3, and then minus 21 over 64, and I expect a negative answer. Okay, so my answer is negative. Okay, so the distance then traveled is 1125 over 64. So my total distance traveled, hence find the total distance traveled. It's 21 over 64 plus 1125 over 64. It's nice they've actually let us into solving these questions. So you need to know why they're asking you to do certain things. Okay, my final answer here is 573 over 32 meters. Okay, so they've really led the question, like they've given you a lot of information here. This is very important. Basically understanding why they gave you this information, because you know you're going to have a positive area if you integrate above the x-axis or the t-axis, and a negative area if you integrate below the x-axis. Okay, and you have to split it up between positive and negative, otherwise you're going to get displacement instead of distance. Okay, so it's really helpful just to know that type of theory. Okay, let's look at question 6. So a car of mass 1,800 kgs is towing a trailer. Okay, it's in a straight road and it's inclined at alpha. Okay, so we've got a car and we have a trailer. Okay, that's how many kgs. The car and the trailer are connected by a tow bar, which is light and rigid. It's parallel to the road. There's a resistive force of 800 on the car. So make sure you get the right thing on the right vehicle. And F acting on the trailer. The driving force of the car's engine is 300 Newton. Okay, because we're on an incline, we also need to include the weight components of the car that are going down, the car and the trailer. Okay, it is given that F is 100. Okay, find the acceleration of a car and the tension in the tow bar. Right, I think I'm going to look at this as a system, so I'm not going to look at the tension in the car yet, but I do know I've got my two weight components going down. mg sine alpha, mg sine alpha. So if I look at the whole system, all of these forces that I've now drawn on here, I've got minus 100, minus 800, minus my mg sine theta for the trailer. 1.5, my sine alpha actually is that, minus 18000, and then my sine alpha. And then my driving force looks like I've written it down wrong. 3,000 Newton. Okay. That is all equal to a mass of 1800 plus 300 times acceleration. So I can work out acceleration directly if I look at the system of the two connected particles. Okay. So I've got minus 100, minus 800, minus 18000 times 1.5 plus 3,000. Also wrote it down incorrectly here. Okay, and that is divided by 1800 plus 300. Okay, so we have an acceleration of 0.5. Okay, find the acceleration of the car and the tension in the tow bar. Right, so now I can look at either one. If I just look at my trailer, I've got 100 going down. I've got my 3,000 times 0.05, and I've got tension acting up. Okay, so minus 100. Okay, so remember what I'm doing here, this is Newton's law. Newton's second law. Sum of forces is mass times acceleration. So I've got the sum of my forces is my friction and my weight component acting downwards, my tension's acting up, the mass of the trailer only because I've just isolated the trailer. Okay, and if I was to get my t on the other side, I just want to double check this. Minus 100. I don't think I included my 1000. No. Oh, goodness. That's what I've done incorrectly. It must be 300 times 0.05. Okay, cool. And this is 150 plus 250, and that gives me a tension of 400 Newton. Okay, cool. Something just looked a bit out of proportion there, so that looks much better. So maybe a note just to make, and it's easy to make mistakes. I'm busy making them now. On this side, you need your mass, and on this side, you need your weight. Okay, so just always check that. Here I've got my 3,000, my 8,000, and here I've got my 18,000. Here I've just got 1,800 and 300. Right, so very important for these questions. Okay, find the acceleration of the car and the tension in the tow bar. We have done that. Part B. It is given instead that the total work done, okay, so we're jumping into an energy equation. Work done against F in moving a distance of 15 meters up the road is 600 joules. Okay, so the work done against, this is not just for the trailer, against F is 600 joules. Okay. All right. So when we're looking at energy, find the speed of the car at the start of the thing is 20 meters per second. Okay, use the energy method to find the speed of the car at the end of 50 meters. Okay, so energy, we're looking for potential energy, kinetic, work done against friction, and work done by driving force. That's my checklist. So my potential energy, kinetic, work done against friction, and work done by driving force. Now I set up my equation of what energy do I have and where's the energy going. Okay, so if I look at this, in the beginning, I have some kinetic energy. I don't have potential energy because I'm at the bottom of a hill. Okay, I need potential energy to get this car going up the hill. Okay, I do have kinetic energy in the beginning, and I also have some kinetic energy at the end because they want me to find the speed of the car at the top of the hill. Okay, work done by driving force is always given to the car. So work done is the same as your driving force times your distance. That's parallel. So in this case, do we have a driving force? We do. The driving force is 3,000 Newton. Well, let me rather write here work done by the driving force, and then we are losing energy to friction of the trailer, and we're losing energy to friction of the car. Friction of the car. Okay, so we just need to see where is the system getting energy from and where is it going. We're getting it from the driving force and from the initial kinetic energy, and it's going to getting the car up the hill. We don't know what the speed is after. We don't know if it's going to be fast or slow. We'll have to take that into account. And here it's friction, that we're losing energy for the trailer and we're losing energy because of the car. All right, so now I've got a half mv squared plus my driving force times my distance. That's my mgh. Okay, work done against friction. Okay, so they gave us that is 6,000 joules for the trailer. And for the car, we know it's got a frictional force of 800. And it's also going for a distance of 50 meters. Okay. Okay, the speed of this is a combined speed. The speed of the car at the start is 20. So now we've got a car and a trailer. They both have the same speed, otherwise it wouldn't be a rigid tow bar. Okay. So 2, 1, that's the mass of my car and my trailer. Then we've got a driving force of 3,000 Newton. And it is going for 50 meters. Okay, then we've got our mass. So we need to take the full mass times gravity and our change in height. Okay, let's just quickly look at our change in height. Sine of theta, sine alpha is opposite over 50. So my height is 50 times sine alpha, which is 0.05. 50 times 0.05. Okay, half my mass, my velocity squared, that's my one unknown. Okay, right, lots of calculating going on here. Let's just see. I might just write these out individually just to keep track. So 420,000. 6,000. Okay, now be careful of all the zeros. Okay, and I get my final speed, not squared, my final speed is 21.2 meters per second. Okay, so some students like to work these all out individually. My trick with this is just working out where does the energy come from and where does it go to, and then just having your checklist on the side. And also to realize that a driving force always gives energy to the system unless they give some sort of special information. And then friction always takes energy from the system. Okay. All right, this is now our last question. And I'm seeing what probably is going to be momentum on a slope. Okay, let's see what it has to offer us. So the diagram shows two particles, P and Q, and a line of greatest slope of the plane ABC. Particles Q, P and Q are each of a mass of m kgs. Okay, so they both have the same mass. The plane is inclined at theta to the horizontal. Sine theta is 0.6. Okay, the length of AB is 0.75. The length of BC is that. The section AB is smooth. And the section BC is rough. Okay, the coefficient of friction between the particle and between each particle in the section BC is 0.25. Okay, so it's the same for both particles, which is helpful. Particle P is released from rest at A. Okay, at the same instant, particle Q is released from rest at B. Okay, so they're released at the same instant. Verify that the particle P, okay, wait, so let's just think about this. Particle Q is going to be going down a rough section of the slope, and particle P is going to be going down a smooth section of the rope. They have the same mass on the same hill, so that's what's going to be coming up with the difference as to why these particles moving differently. The one is moving on a rough slope, while the other one is moving on the smooth slope. Okay, verify that the particle P reaches B 0.5 seconds after its release with a speed of 3 meters per second. Okay, so we just tackle this one thing at a time. It does look like it's going to get complicated, but let's just do one thing at a time. So verify that particle P reaches B 0.5 seconds after it's released with that speed. Okay, so if we look at particle P, we know its initial speed is 0. Its distance is 0.75. If we look at a time of 0.5 seconds, what is the speed? So that's enough information. So we're not looking at acceleration right now because the problem is we don't have the mass of this thing. Okay, so let's just verify it. Because they use the word verify, we can plug in the information and see if we get the right answer. Okay, so I'm just quickly going to go to my equations of motion. So I've got S is equal to half U plus V times T. Okay, and if I just look at this, I've got 0.75 times 2 divided by 0.5, and that gives me a velocity of 3 meters per second. Okay. All right, so that seems to be verified. Let's jump on to our next question. Find the time it takes from the instant the two particles are released until they collide. Okay. Right, so I just want to see if this information is all true, then I can probably also work out the acceleration of this particle. So I don't know if that's what I need to do, but I'm just going to start there. Okay, so V is equal to U plus AT. I know it's reaching at 3, it starts at 0. I don't know what my acceleration is, but I can figure it out now. So 3 divided by 0.5, so 6. My acceleration is 6 meters per second squared. Okay, so particle P is going down at 6 meters per second squared. Okay, let's look at particle Q. So this has got its mg sine theta pulling it down, and it's got its frictional force pulling it back. Okay, I wonder if we could work out, if I look at P, sum of my forces is mass times acceleration. The only force that this thing has is mg sine theta pulling it down. Okay, so we can take out our mass. It's 0.6. Okay, 10 times 0.6. Okay, this is unhelpful information because we already know that. Okay, so I'm just busy processing what am I supposed to be doing here. Find the time it takes for the instant the two particles until they collide. So I was hoping to actually find the mass there. That's what I was hoping for. But anyway, okay, if we look at particle Q's got its mass going down and its friction pulling it up. Okay, so we know it's minus friction plus mg sine theta is going to be a specific mass times the acceleration. My friction is mu times r. Okay, what I can see here, my r is just going to be opposite. This is very interesting. My weight component. So my r is mg cos of theta plus mg sine theta. I think I'm busy using theta. Oh no, it is theta, that's fine. Okay, this is so interesting. Can you see my m's are not even needed. So I am going to be able to solve this without even having a clue as to what the weight is of this thing. Okay, my mu is 0.25, gravity is 10, and then cos of the inverse of sine of 0.6 plus 10 of 0.6 is equal to my acceleration. Wow, this is cool. Okay, nice to know this type of sum. Good to practice it. 25 times 10 times cos of the inverse of sine of 0.6 plus 10 times 0.6. So this has an acceleration of 4 meters per second squared. Okay, cool. So that's less than 6 meters per second squared. So that is at least good to know. Okay, so what we can see now is that the mass is actually irrelevant for these types of questions. I have actually seen that before, but what we are going to say now is that when P hits the rough patch, it's basically going to slow down to 4 meters per second squared in terms of its acceleration. Okay, let's just orientate ourselves now. We know what the acceleration is on the rough patch, and we know what it is on the smooth patch. So they say find the time it takes from the instant the two particles are released until they collide. Okay, so particle P reached B after half a second. So I just want to know, where is P at that point? So not P, where is Q? So Q started from rest. It's accelerating at 4 meters per second squared. I don't know where it is. I want to know where it is, and in the time of 0.5 seconds. Okay, so my S is equal to UT plus half AT squared. That gives me a distance of 0.5 times 4 times 0.5 squared. That gives me a distance of 0.5 meters. Okay, right, so I'm just going to redraw this. At a certain point, when P is now here, Q has already moved 0.5. So this is Q, and that's P. Find the time it takes from the instant the particles are released. So this is 0.5 seconds later. Okay, so maybe we must work out what is the speed. No, let's just go particle P. I'm just going to shift this down here and make another column for myself. Okay, so particle P now has an initial speed of 3 meters per second. Now it's accelerating at 4 meters per second. It needs to go a distance, so they're going to collide somewhere over here. So it's going to go whatever the distance is. I'm just going to say it's going to go at a specific distance, S, and a specific time, T. Okay. Ooh, I'm running out of space here. So it's going a specific distance. It's starting at 3. It's got time, half times 4t squared. Okay. And then my Q particle, it is going at a speed. I'm just going to work that out of here. Okay, I would probably definitely need to be using the additional page right now, but anyway. 4 times 0.5, so that's 2 meters per second. So it's got an initial speed of 2 meters per second. It's now accelerating also at 4. it is going to have a distance of s minus 0.5. So it doesn't have to go that extra. So it's going s and then minus the 0.5. It doesn't have to travel that part. So as long as you can make them relatable to each other. T is t. Okay, so s is equal to ut plus a half at squared. So s minus 0.5 is equal to 2t plus a half times 4 times t squared. Okay. Two t squared plus 2t plus 0.5. And here I've got an s. Oh my goodness. So now I'm going to do a simultaneous equation between the two. So 2t squared plus 2t plus 0.5 is equal to 2t squared plus 3t. Okay, those can cancel out. That's really nice. My 2t I'm going to take to the other side, so I just get t, and that's 0.5. So they're going to collide at 0.5 seconds later. Okay, that's good to know. And so if I plug that value into any one of my s's, that's a half times t is basically 2. Okay, so here I've got 3 times 0.5 plus 2 times 0.5 squared. That gives me a distance of 2 meters. Okay, so initially, what did they want to know? Find the time taken. Oh, find the time taken from the instant they released. So I didn't actually need to know that distance. This is 0.5, so they initially moved 0.5, and then P was on the rough as well, and then they collided after another 0.5. So in other words, the time that they took was 1 second. T is equal to 1 second. Okay, if I were to redo this, I would try and write smaller, but they weren't very gracious with their space. Okay, but we have an answer of 1 second there. Okay, once again, just to start somewhere would be my encouragement. Don't just look, but start calculating, start puzzling things together. I mean, I did something here and then I realized there was no point in it. It's okay. Rather just start putting the puzzle piece together as much as possible. And then just take note of this thing that you don't need to know the mass of the particle to be able to calculate the acceleration. So just note that. Okay. Right. Let's go. The two particles coalesce. Okay, wonderful. When they collide. Coefficient of friction between the combined particle is still that amount. Find the time it takes from the instant the particles collide until the combined particle reaches C. Okay, right, the instant. So now we notice that they collided 2 meters down. Okay, so it was not irrelevant that I calculated that. 2 meters down. So that means these particles are now traveling only for 1.25 meters. Okay, and now they collide. So we also got to figure out at what velocities they're colliding. Okay, and the time it takes two particles coalesce when they collide. Okay, yeah, so we really are going to have to do a lot more stuff here. Okay, so I'm going to jump into these super equations, but I'm just going to calculate now my final velocity. So for P is equal to U plus AT. I've got my initial velocity of 3, and then we know there was just a time of 0.5. So 3 plus 4 times 0.5, so that's just giving me 5 meters per second. This is now just as they're about to collide. Q, let's just also do V is equal to U plus AT. I'm not listing everything because I've listed it above. So I've got my U 0.5, so 2 plus 4 times 0.5. That's 4 meters per second. Okay, so now they're colliding at 5 and 4. They're both going down. So they're both going in the same direction. Momentum direction is important. So my mass times 5 plus my mass times 4. And then they coalesce. 2 times mass by velocity. Two particles coalesce when they collide. Okay. Right, what we can see here is that mass cancels out once again, which is pretty cool. Okay. So my velocity after the collision is 4.5 meters per second. Okay. Now these coalesced particles are going down. So my U is 4.5. My distance is 1.25. My acceleration we're going to have to figure out, and they want to know the time. Okay, so because mass doesn't actually count, acceleration is still going to be 4. Interesting. Okay, so here we've got 4.5 times my time plus a half times 4 times squared. So I've got 2t squared plus 4.5t minus 1.25 is equal to 0. And if I solve that, okay, I'm going to be using my quadratic equation. And I am getting time of 0.25 seconds. Obviously, we can't work with negative time. Okay, so I just want to check, yeah, my distance was 1.25. Okay, and that will then be the time that it takes. So I find part C was actually much easier than part B, even though part B was more marks. But maybe it's just for accounting for the momentum equation and then Suvat. So that is the end of the paper. Nice paper. Send me your thoughts. I don't know. It does feel like they're creative in the way they're asking questions these days. So I definitely think it's worth going through this paper, going through each of them before your exams. So all the best. I hope that it goes well.